Nuclear waste. It's dangerous for centuries. It needs to go away. And now, it will. One, two, three. Shoot! 1, 2, 3. What am I doing wrong? 1, 2, 3.
Boy, if only it were that easy. Now, the persistent paradox that is nuclear power. It's efficient. One train car full of nuclear fuel can keep a nuclear power plant running for a year. But it takes a whole train load of coal every day to keep a conventional power plant running. There are a lot of things to be afraid of when it comes to nuclear power. There are meltdowns where the uranium metal fuel gets so hot that it burns a hole through the reactor and the whole thing explodes. There are terrorists who could get hold of some of this nuclear material and make the events of September 11th look like getting a parking ticket. The real terror, the real danger, the real horror of nuclear power may come long after the power is generated with nuclear waste. Now, do science and society have an answer for this problem? Well, let's have a look. Let's have a look. Let's have a look. Let's have a look. Let's have a look.
He went from science sweetheart to nuclear skid row. Hear about his rise, fall, and valiant climb back on The 9 True Science Story. After World War II, America found a new hero. A hero whose name would be known around the world. Our friend, the atom.
I was young and cocky. You know how it is. When you're young, you think you can do anything.
Indeed, his future seemed limitless.
That stuff was made up by the press and my promoters. I never said I could do all that stuff.
The 60s generation turned against Mr. Atom.
All of a sudden, I'm not the friend anymore, you know? All of a sudden, I'm not cool. That really messed me up. There's not a day goes by that I don't wish I could go back and change all those errors. I'm sorry. I'm sorry. Can we stop? I need a break. Just a sec. It was rough. I thought I was all bad. There's been some mistakes in the past, but I'm not ready to pull the plug just yet. America still needs me, and I'm going to find a way to be our friend, the atom, again.
This is the Columbia Generating Station, the only nuclear power plant in the Pacific Northwest, but there are 103 nuclear power plants in the United States operating today. The big tall building's the reactor, the big lower building is the generator, and the round buildings near us are the cooling towers to keep the steam going through the electrical generating cycle. At a nuclear power plant, everybody who comes in gets checked out by guys like these. It's a pretty secure place. Under here is the reactor. 30 meters down, when the reactor's running, there's uranium fuel making heat. This is a classic demonstration of a nuclear chain reaction, the kind of reaction we have in a nuclear reactor. The mousetraps represent uranium atoms that we get by digging up ore from the ground, and the ping pong balls represent the subatomic particles called neutrons. Now, to start a chain reaction, we bombard the uranium atoms with extra neutrons, or in this case, an extra neutron. The reason this nuclear chain reaction is possible is because uranium has the rare ability to absorb a neutron, which will make it split or fission into smaller fragments. As uranium splits, it releases a lot of energy in the form of heat. It also spits out a neutron of its own, which can bombard a neighboring uranium atom, which then itself fissions, releasing heat and zinging out another neutron, and so on and so on. In the reactor, the heat created by fissioning uranium heats up water, making steam. This high-pressure steam blows on the propeller blades of a turbine, which spins the shaft of a huge generator. Now, in the generator, a coil of wire is spinning in a magnetic field, which makes electricity. So it all boils down to this. The reactor, the steam, the turbine, the fuel, everything is set up to drive this big generator. It turns 30 times a second and makes electricity for close to 3 million people. It makes 1.2 gigawatts. It's a lot of juice. A nuclear power plant can generate a lot of electricity, but in nature, we don't get something for nothing. So when we generate electricity, we also get tons of radioactive waste. How much waste do you make in 60 years?
Well, in 60 years, we would produce enough waste to basically fit contained into a convenience store.
That's not very much.
Well, it's not very much when you compare it to like a coal plant where, you know, its waste of all the coal that it uses and emissions into the environment.
It's probably 10 million times that.
Yeah.
So the stuff is dangerous.
It's dangerous, but it's contained in a small volume.
The fuel rods are taken from there into this pool. This is where they're stored for years. When they first come out, they're too hot to handle. They cool off, and then they're eventually taken to dry storage. There are reactor pools like this all over the world, just waiting for a place to put the waste. What is this, Larry?
This is a dry cask storage for spent nuclear fuel.
Is this radioactive?
There's radioactivity inside it. We've got concrete overpack that protects us from the radiation.
How thick is that?
Oh, it's about 22 inches. Total about 24 inches, including the steel.
You can just stand right next to these. You can touch these.
Oh, yeah. It's completely safe. And you can see by looking at the meter, it's less than 1 millirem per hour on contact.
Barely a millirem.
Per hour.
Put that in perspective. What's a dental X-ray? 20?
Dental X-ray is probably about 20 millirems.
So right up next to it, it's less than an X-ray, which is only on for a few moments.
Yes.
Right. Suppose we just left it here. How many years or centuries would it take for this stuff to become benign?
The current average estimate is about 10,000 years.
10,000 years.
Yes.
That's a long time.
Yes, it is.
There's something about these that doesn't look like they're good for 5,000 years.
No, they're not.
Yeah. Radiation is technically any energy that radiates. So light, heat, microwaves, and radio waves are all radiant energy. Now, this type of energy is often easy to contain. Microwaves can be contained with nothing more than a metal screen. Light can be blocked with nothing more than a piece of paper. The more paper you have, the more blocking you get. Now, in nuclear reactions, our problem is what we call ionizing radiation. Ionizing radiation can smash into the tissues of living things and disrupt our cells.